At time of release, it is just 2 weeks until your first A-level maths exam, and just a feeling, but I reckon there'll be some calculus on there. So pause the video, see if you can have a go at these 6 problems, and the solutions will follow shortly. Right then, let's get into problem number 1. So we have x times 2x minus 1 to the power of 5. What we have here is a function of x times another function of x. So what we're going to do here is use the product rule. Now remember, the product rule is something that you don't get given in the formula book. How it works is that you need to do the first function of x times the second function differentiated, add the first function differentiated times the second function of x. So I'm going to call the first function u. So I'm going to let u equal x, and I'm going to let v be 2x minus 1 to the power of 5. So as I mentioned, we're going to do the first function of x times the second one differentiated, add the second function differentiated times the first one differentiated times the second function. So what I'm going to need to do is differentiate both of these. So I'm going to find du by dx, which is just 1. And I also need to find dv by dx. Now, if you can do this quickly, that's absolutely fine. I'm just going to go over again how we can differentiate functions like this, and we can do that via the chain rule. So what I'm going to do is I'm going to call this bit in the bracket here w. Okay, usually I would use u, but we've already used u elsewhere, so I'm going to use w here. So that w is just 2x minus 1. Okay, so basically I'm just letting the bit in the bracket equal w. So what I'll need to find is dv by dw. So differentiate differentiate v with respect to w, which gives us 5w to the power of 4. And I also need to find dw by dx. That's just going to be 2. So I want to find dv by dx, so if I multiply dv by dw times dw by dx, the dw's cancel, which gives me 10w to the power of 4. But we want it in terms of x, so let's just put that w equals 2x minus 1 back in. And there we go. So dv by dx is 10 times 2x minus 1 to the power of 4. Now, if you've done quite a few of these now, hopefully starting to spot a little pattern here that every time what we're doing with these ones of the bracket is we're multiplying by the power, and then we're multiplying by the derivative of the bracket. So in this case, 2. So 5 times 2 for the 10. And then we're reducing the power of the bracket down by 1. Okay, I still like to show that with the chain rule just so you can see everything that's going on there. But as you get quicker with this, you can use these quick little tricks. So let's actually put this into the product rule. So to find my dy by dx, I do the first function, which is x, times the second one differentiated. So that will be 10x times 2x minus 1 to the power of 4. Okay, so I'm just timesing these together here. And then I'm going to add the second function times the first one differentiated. So I'm just doing 1 times 2x minus 1 to the power of 5. And this question didn't ask us to do any simplifying, but sometimes questions might ask you to put them in particular forms. So we can actually write this as a product. So the way we can do that is we can notice that we've got a common factor of 2x minus 1. In fact, I've got a common factor of 2x minus 1 to the power of 4. So then I just look at both of my terms and think, well, what have I multiplied 2x minus 1 to the power of 4 by? Well, the first case, that's just going to be 10x there. And then if I look at the second term, well, I've got 2x minus 1 to the power of 4 on the outside. So to get 2x minus 1 to the power of 5, I just have to multiply by another 2x minus 1. You can then simplify in that bracket, and that's an alternative way that we could leave it. And questions could ask you to show that this differentiates to be something in the form 2x minus 1 to the power of n times ax plus b, where a, b, n are constants that you need to find. So, it is quite common that a question could ask you to do, write it in particular form at the end. Okay, let's look at question number 2. And one thing we haven't seen so far is differentiation from first principles here. Now, please only do this, okay? Only do this if the question actually says prove from first principles. You certainly wouldn't want to be doing it with some really difficult function in your exam, okay? So usually differentiation from first principles, it should be something that is relatively simple to differentiate normally, but you're going to go through the proof of how that actually works. So the formula for differentiation from first principles, it is in your formula book. Okay, so this is in your formula book. Please use it. Please look it up if the question mentions differentiation from first principles. So what we have to do is we need to figure out what f of x plus h will be. Okay, so there's an f of x plus h in our formula. So we're going to need to figure out what that is. Okay, so f of x is 4x squared. So f of x plus h, well, what I need to do there is where I see x, I now replace it with x plus h. Make sure that x plus h is in a bracket, okay? Because you need to make sure that you're squaring all of the x plus h. Okay, and then timesing it by 4. Not doing 4x plus h in a bracket all squared. Doing x plus h squared and then timesing it by the 4. So, expand out the x plus h. And then I'm just going to times everything there by the 4. So, I'm just doing this to the side here. So I know what my f of x plus h is, and I can just put that, I've already done the expanding, and I can then just put that into my formula. So f dash of x, as the limit of h approaches 0. So I put in there the f of x plus h that worked out there. Don't forget to take away the f of x. I do quite commonly see people forget to take away that f of x because they think, oh, I've done all the algebra with the f of x plus h. There's lots of stuff happening there. But they can sometimes just forget to take off that 4x squared. Okay, and that all gets divided by h. So let's start looking at the numerator there. And I can see that the 4x squareds are going to cancel. Okay, so just left there with the 8xh plus 4h squared. And now what I'm going to do is divide both of those terms on the numerator by h, which leaves me with the following. And when we get to here, we're going to look at what happens as h tends to 0, okay? Basically, we're just looking at a general point on our curve and a point that is a very tiny distance away from it. And the line segment the gradient of the line segment of those 2 points that are really close together is going to match the gradient of the tangent at that point. So as h tends to 0, what's going to happen is that 4h is going to tend to 0. Okay, it's not 0, but it's so close to it. So 4 times a number that's virtually 0, not actually 0, but it's almost 0, is just going to also tend to 0. So as that happens, the 4h tends to 0, we just get left with 8x. So we just need to make sure we clearly state our result that f dash of x equals 8x there at the end. So if you've not done differentiation from first principles in a while, there we go. Please don't just go, oh, 4x squared. Well, it's just 8x. I know that. Make sure that you use the formula there. But please don't use that if it doesn't actually say use first principles. It could get quite messy if you do that. Speaking of messy, let's have a look at this next one. We've got y equals natural log of tan x squared. Okay, so how can we approach this one? Now, it might be just tempting to start off by looking at the bracket and going, oh, well, I'll let the bit in the bracket be u. I'll use chain rule. But what I'm going to suggest we do first is use our laws of logs to bring that power down first. Okay, so I'm going to make this 2 natural log of tan x to begin with. Admittedly, you could do this at a later stage if you do make a substitution, but I'm just going to get this done nice and early here. So I'm going to let the bit in the bracket there be u. Okay, because what we've got is a function within a function. Okay, we've got natural log of something, which is a function, and then tan x is a function itself. Okay, so y is going to be 2 natural log of u, where u is tan x. So we're going to use the chain rule here, because I've got a function within a function. Now, if you differentiate natural log of u, that will be 1 over u. So 2 natural log of u will be 2 over u. Okay. Knowing the result of differentiating natural log of u or natural log of x is something that isn't in your formula book. It is a really, really important one to learn. We're also going to do du by dx. So we're going to differentiate tan x with respect to x. This one is in our formula book, and it is sec squared. Okay, so you do get given that one in the formula book. I'd always recommend when you're doing calculus problems, have the page open at the differentiation or integration section, just so you can just double check, oh, do I actually get given this along the way? So I want to find dy by dx. So I multiply dy by du and du by dx together. But your u is just tan x so this is what dy by dx will be. But yet again, we could get us to do more with this. Okay, so whilst the main focus of this video is calculus, let's do a little bit of simplifying along the way, because that is also, whilst calculus is a very big component of your pure papers, there's going to be a fair bit of trig in there as well. So let's see if we could write this in a different way. Again, you want to maybe pause here, have a go at seeing if you can write it as a single trig function. Pause it, have a go, and I'll show you how I would go about it in a second. So sec squared is the same as 1 over cos squared. So 2 sec squared, I'm going to write that as 2 over cos squared. And I'm dividing that 2 sec squared, or that 2 over cos squared, I'm dividing that by tan x. Now tan x is the same as saying sine over cosine. So often it helps to have things just in sines and coses, just because then you're only dealing with two functions, and then there's links, lots of links with sines and coses, as we'll see in a second. So sometimes it can just help to do that. So if I'm dividing by sine over cos, that's the same as multiplying by cos over sine. And what happens there is you can cancel out some cosines there, and this is going to leave you with 2 over sine x cos x. Now, whenever I see sine x and cos x together, maybe this is just me being weird, but I kind of have an alarm that goes off that thinks I've got sine and cos next to each other. I immediately start thinking about sine 2x in some way. Okay? Because 2 sine theta cos theta, or 2 sine x cos x, is the same as sine 2x. Now, we don't have 2 sine x cos x, we just have 1 sine x cos x. So instead of this just becoming sine 2x, that's what it would be if there was 2 sine x cos x on the denominator here. I've only got half of that because the 2's not there, so that would just be a half sine 2x. Finally, 2 divided by a half is just 4, and 1 over sine 2x is the same as cosec 2x. So that is how we could simplify our answer. Which, I wouldn't have expected that when I wrote this. I wasn't sure what was going to actually come out of the end. I was like, okay, cosec has come out of this. Okay, it's weird. You've got to start off with natural logs and tans, and you end up with cosec. That's just how it works sometimes. And with that, that is our last differentiation problem. What we're going to do now is we're going to look at some integration problems now. So, question 4. We've got f dash of x, and we're asked to find f of x, and we're given that 1, 2 lies on f of x. So if we've got f dash of x and we want to find f of x, we are going to need to integrate. So before I just dive straight in though with integration, I should ask myself, can I simplify this first to help me integrate it easier? Okay, which I certainly can do. So, to help me make this a little bit easier, I'm going to separate this up, and I'm going to use some laws of indices to help me do that. So, firstly, I'm going to do 2 divided by 5 root x. So I've got 2 divided by 5 in terms of the numbers, and then I'm dividing by a root x here, dividing by the square root of x. So dividing by root x, which is the same as dividing by x to the half, is the same as multiplying by x to the minus a half. And having it in that form is going to be a lot easier to integrate. Then we're going to do 7 divided by 5. Deal with the numbers first, and then deal with the x's. You've got x divided by x to the half, which just gives you x to the half. Okay, that x is essentially x to the power of 1 divided by x to the half. Take away the powers. 1 take away a half. It's just a half. Now that is all ready to go and be integrated. So I've got f dash of x. If I integrate that, it's going to give me f of x. So we just go to each of these terms, add 1 to the power, and divide by the new power. Okay, if I do 2/5 divided by half, it's the same as doing 2/5 multiplied by 2. Second term, add 1 to the power, divide by the new power. So add 1 to the power 3 over 2, divide by the new power, divide by 3 over 2, or multiply by 2 over 3. And if we stop there, we'd be doing a very bad thing. This is an indefinite integral, so we need to put our plus c. But we can actually find what the c is here because we're told that 1, 2 lies on f of x. Okay, there's a reason why they've given us that piece of information. Okay, think what you want of examiners, but generally they don't, things they give, information they give in an exam, it should be all something that they intend for you to use at some point. So we know that when x is 1, f of x is going to be 2. So we're going to replace the f of x with 2, and we're going to sub in x equals 1. Always good when we have to sub in x equals 1. Just makes things nice and easy when we only have to substitute in 1. So then we're going to, when we work that out, we'll get c as 32 over 15. So f of x, and you should always write this out in full at the end with the plus c in there. The following. Okay, 2 more to go. See, again, we've not really had a problem like this one so far. So I thought, we haven't really done anything with area in this series. So let's have a look at this question where we've got to find the finite area bounded between the curve y equals 9x minus x squared and the line y equals 8. So what I want to do first is just do a little sketch of the problem to see what actually do you want me to find. Now, usually in an exam, you get some sort of sketch here, but I think it's worth, doing a problem like this. We actually need to set up the sketch ourselves. That can't harm at all. So, firstly, I'm just going to factorize the x out for the equation of the curve, just make it a little bit easier to sketch. So I can see there I've got roots of 0 and 9. And because it's a minus x squared, it's going to be an upside down quadratic. Okay, south face quadratic because it's negative, if you will. And we're going to look at where it crosses with the line y equals 8. Okay, which is going to be somewhere here. Okay, it's just a horizontal line that goes through 8. You can check, by the way, that the line is going to be below that maximum point of the curve, because if you substitute in 4.5, so x is 4.5 into the equation of the curve, then you'll see that actually the maximum point is greater than 8. So what we're trying to do is trying to find this area here. Okay, let's call that R. Okay, you're trying to find that area there. So what you will need to do, though, is you'll need to find where the line and the curve cross. So we're going to do this simultaneously. So I know that 9x minus x squared equals 8. Okay, so this is where the y coordinates are going to be the same. Okay, and I'll just rearrange that to get a quadratic. Solve that quadratic. And we can see that it crosses when x is 1 and 8. So now I've got all the information I need to start to integrate. Now there are a few ways that you can go about this. Because we've got, we're looking at area between a line and a curve, what I can do is, because the curve is above the line, when I set up the integral, I can do the curve 9x minus x squared, take away the equation of the line. Okay, so you can do it separately. You can do the equation of the curve separately and then take away the equation of the line separately, or in this case, just work out the area of a rectangle. That would also be absolutely fine here, but I'm just going to do it this method where we can just do the curve, take away the line to find that region there. And my limits are going to be 8 and 1. So we just integrate this now. So go through each term, add 1 to the power, divide by the new power, add 1 to the power, divide by the new power. And when you have the 8, it just basically becomes 8x. We still essentially are still adding 1 to the power. It's just that that power was 0 before, so now it's 1, and you divide by 1. So that's why we get 8x there. And I've got limits there of 8 and 1. So substitute in the 8, substitute in that upper limit, and we get 160 over 3. And then what we're going to do is take away the lower limit, so take away the 1. And then just work that out to get 343 over 6. And with that, there is just one final problem. Okay, one more problem and then we're done. You're done with your Calculus 6 for the week. Apologies, that has been a little bit more than a week since the last one. So we've got our last problem then, cos squared 4x. So whenever I'm asked to integrate sine squared or cos squared, it's not as simple as, oh, just add the power by 1, divide by the derivative of the bracket. It doesn't work like that, okay? So when I see sine squared or cos squared and I'm asked to integrate it, immediately think about your double angle formulae. In particular, your double angle formulae with the cos 2 thetas. So from your trigonometry, you should be able to recall that cos 2 theta is 2 cos squared theta minus 1. Okay, you can just derive that from the addition formulae in the formula book, but this is something you don't get given, so you don't get given it in that form. You can derive it from what's in the formula book, but you don't get given what I've just written there. So you can rearrange this to get that cos squared theta is just a half cos 2 theta plus a half. But in our problem, we don't have theta, we have 4x. So replace the theta with the 4x. So on the right hand side, you don't have 2 theta anymore, you have 8x. So now this is ready to be integrated. Okay, but please, if you see a cos squared or a sine squared, use your double angle formulae to sort it out before you go ahead and integrate. Okay, so integrating this, when you integrate cos, it goes to positive sine. So we're going to get a sine 8x and then divide by the 8, which will give you 1 over 16. The half just becomes a half x. And are we ready to finish the video there? Because I hope you're just thinking there's something else I need to do before we sign off. And of course, it is put the plus C. Let me know how you got on with the problems. Are there any problems that particularly you want to see more of in the lead up to the exams? We are getting very close now. Let's say at time of release, it's 2 weeks away. So if there's any particular problems you want me to cover in the next couple of weeks, let me know. I'll try to, in a couple of weeks' time after the first paper comes out, I'll try and think about what didn't come up on paper 1 to kind of focus the video more on paper 2 stuff. So hopefully that will be useful. But let me know how you got on, and see you next week for another 6 calculus problems.